this will vary from computer to computer, but imagine that you have a big array, but whose size is slightly, so it's not very symmetrical. So imagine an array that has 4,000 rows, 400,000 rows and 5 columns. If you try to duplicate, if you try to, if you try to add that array to another array, that will take some time. But now imagine that you have the transposed version. So instead of being 400k columns times 5 rows, it's 400k rows times 5 columns. And what you see, if you do this exercise, so you take 2 arrays and you sum them, and they are exactly of the same overall size, but they are transposed, and they are physically transposed. So you do a transposed copy. You cannot do a transposed view. If you have one array 400k times 5 and another 5 times 400k, and you try to sum it to a similar array, you will notice that the time to do this, though they are the same, they have the same number of elements, they have the same overall size, you'll notice that one of them, it will depend on the operation, but very easily 2 times to 10 times as fast as doing the operation with the other one, which is apparently quite strange, because they have the same number of elements, right? And you are doing the same operation. But the issue has to do with representation in memory. So if you have every row contiguous, it means that the CPU gets the first element, then gets the second element and the third element. But when it goes and gets the row, it gets it from here, then it has to go very, very, very far away in your linear memory to get the next row. And what this means is that your RAM is being, when you go to do the next operation, your RAM needs to bring an element from another part into the CPU. Your CPU needs to bring RAM into its cache that's different. So it will need to say, okay, CPU, send me through the bus this other block of RAM. But if you are working in the same row and not in the same call, if you are going column by column and not row by row, what happens is that the CPU asks for the block and says, "Oh, I already have this block, so I can use the local CPU cache," and the local CPU cache can be orders of magnitude faster than the RAM. So sometimes just transposing the representation can easily increase your performance. And if you go to NumPy, you will see that they have Fortran and C representations for the arrays. And what happens there is C, it is row contiguous, whereas Fortran is column contiguous, or vice versa. But one represents first column, second column, third column, and the other represents first row, second row, third row. And if you know that your operations are more row inclined or column inclined, if you choose the correct representation, because of the CPU cache effect, you can very easily get very increases in performance. That is why, for example, some compressed formats of arrays and are faster than uncompressed formats, because you bring a compressed block, you uncompress it, and then you are able to process it. And the cost of uncompression, believe it or not, for fast uncompressed algorithms that are fast and local, the uncompressing of a CPU block in cache is faster than bringing more blocks of an uncompressed version. So sometimes you see this effect where a block where you see this effect where a compressed version is actually faster to process, even with the cost of uncompression. I would recommend you to look for a library called BLOSK, where they have a very good, I'm going to put the link in the chat, where they have a good explanation for this. They have a very good explanation for this. I'm just making sure. I think it's this one. If you go to the documentation, you will have where they essentially use. Oh, for a second. Okay, and okay, I think it's that one, and you have that effect. There is another library called NumExpert that uses similar, and I'll go through to that in the book in more advanced parts, where using expressions, where you can use expressions to take advantage of CPU cache locality.